So in theory, you already wrote down the equilibrium constants, because I gave you a little bit of a head start. You had since last Wednesday to work through it, and I told you kind of starting into this. So we've got our equilibrium expressions. We're going to go through each of these and talk about some of the details. So in that first one, what is special, unique, or different from what we've seen in the past about our first equilibrium expression? Nothing?
Coefficients become the exponents.
Yeah. So when we dealt with the rate constant, we couldn't bring the coefficients in as the exponents. Equilibrium constants, we do. Okay, so those will go directly into your equilibrium expression. So that's a big change from our rate constants. We got to make sure we keep those straight. Okay, anything else you notice interesting about that black one? I'm hoping not, because that's all I got. Okay, how about the red one? Okay, I do have positive and negative charges in there. Does that really change much about our expression? Because couldn't we have negative and positives in our rate expressions too? Could. So this is a little bit different because we're seeing those charges appear, but those are what make those things what they are. So that shouldn't be all that odd. Anything else? Okay, my turn. What do the brackets mean? Concentration. What is concentration? Moles. Moles of what? Moles of what? Substance. Of your substance. Over liters of what? Of your solution. Okay. So we could look at that. Ballpark would be liters of our solvent. So if we looked at H3O plus aqueous, right? We could look at how much H3O plus was present in what? What's the solution? What does AQ mean? Aqueous. What does aqueous mean? It is not liquid. It's not solution. What does aqueous mean? Dissolved in water. Very, very, very specifically. Okay, because you can have solutions of ammonia. You don't write AQ next to them. AQ is very specifically referring to dissolved in water. Okay? As far as y'all are concerned, for the most part, every solution that you're working with is dissolved in water, so that isn't a huge change. Okay? Why is that important to talk about this? Well, can I have H3O plus dissolved in water? Seems reasonable. How about bromide dissolved in water? HBr? Okay. Can I have water dissolved in water? Okay. You could bring in the whole water is wet argument if you really wanted to. Okay. If we're looking at the concentration of liquid water here, its concentration does not change. It's a pure substance. Because it is pure, that concentration remains constant. And if it remains constant, what should we do with it? What does this whole expression equal?
K.
Capital K. And what was capital K? I think it's at the top of the screen. Capital K is the equilibrium constant. And if water's just going to remain a constant, what could we do? We can remove it from the expression and factor it into our equilibrium constant. Okay? So when we're looking at our equilibrium expressions, we won't use pure substances in them. Because as the pure substance, its concentration does not change. Which takes us to the last one. What's happening in the last one? There's two solids. Okay? And if we're looking at a solid, what is the moles per volume? Is the volume going to change much? No, because the solid occupies just the volume that it occupies, which means its concentration is constant, which means you can again, did I cross out the right ones? Yeah. Factor that into your K expression, which means your K expression for the last one is just the concentration of CO2. Just happened to dawn on me as we're talking through this, if we look at CO2, CO2 is a gas. Isn't that a pure substance? It is. CO2 is a pure substance. Why do we not delete it from the equilibrium expression?
That one changes a lot, like the entropy.
What is our concentration? Moles per volume. If we look at a gas of CO2, can you change the volume and therefore change its concentration? Yes. Okay? Whereas changing the volume for a solid really doesn't do much. Okay? And saying much is a bit of an overstatement. As far as we're concerned, it doesn't do anything. Okay? Kind of makes sense? So this becomes critical to going through and solving your equilibrium expressions because you need to know what goes into it, which then sets us up with another problem. Okay, phosgene is a toxic gas. If we mix, I already forgot the numbers, if we mix 0.1 molar chlorine and 0.1 molar carbon monoxide, we get 0.08 molar phosgene. Okay, 0.02 molar chlorine and 0.02 molar carbon monoxide. Calculate the equilibrium constant. So I want to know the equilibrium constant. Set it up. All right, I'll say that again for the sake of the recording. Where should you start?
Right expression.
Write the expression. Get your expression down so you have something to work with. When is our expression true? When does K equal the concentration of our products over our reactants? At equilibrium. If we're not at equilibrium, this expression is invalid. So it's only true once we've achieved equilibrium. So what does that mean we need to do? We would plug in our numbers. So at equilibrium, we have 0.08 molar of our, I always like including the leading zeros. What's our concentration of our chlorine? 0.02. Concentration of our carbon monoxide, 0.02. Punch it into a calculator and we should get 200, I think, right? Okay. So if we look at that, relatively easy, you just got to put those numbers together in the correct order. How did the question make it more challenging?
The initial concentration.
We also included the initial values, at least of the chlorine and the carbon monoxide. Okay? Why are they included there? They're distractor numbers that you could randomly put in to your expression. So you have to realize when the expression is valid and only use the numbers that are associated when that expression is valid. So you have to ensure you're at equilibrium. Kind of, sort of? Can we make the question more difficult?
Yeah.
Sure, why not? How does this question become more difficult? If you'd memorized the question, you hopefully saw that we've now deleted some information. What we deleted from the question was the concentration of chlorine and carbon monoxide gas at equilibrium. Can we still solve? Okay? And we might go through, well, without those numbers, we can't solve this expression. Okay? This is where what we could potentially do is bring in what you will grow to hate or love, depending on your perspective, I guess. What can be known as an ice table. Okay, this is a relatively simple version of it, and I would assume you'll get more complex ones later on. So what we would go through and do is create a table where we would start off with I for initial. We're going to know our initial concentrations. What's our initial concentration of chlorine gas? 0.1. What's our initial concentration of carbon monoxide? 0.1. What's our initial concentration of phosgene? 0.08. Is it 0.08?
No, it's the.
Nah, 0.08 is the final. What did we start with? 0. If we're not clearly stating what your initial concentration was, guess what the value is? 0. The next thing we would encounter within our ice table would be the C, because we're talking about ice and how we spell ice. Conveniently, we spell it correctly. We want to know how much it changes. In the course of this chemical reaction, what would we expect to happen to the concentration of product? Change the question on you. It should increase. When we're running a chemical reaction, what should happen to our products? They should increase. How much they increase is a different question. We'll address that in a second. So it should go up. It needs to be positive. Ooh, signs. Signs are useful. What should happen to the concentration of reactants? Those need to go down so the products can go up. Those should be negative. Do I know how much the concentration goes up of my product? No, not initially at least. So we'll say X. Okay. Now what I want to do? Well, this is X moles of what? Phosgene. I want to know how many moles of carbon monoxide I would get or need to consume. Can I convert moles of phosgene to moles of carbon monoxide? Yeah, how do I do that? Through a balanced chemical reaction. Moles of our phosgene, moles of our carbon monoxide. If we use the coefficients from our balanced chemical reaction, we know that is 1 and 1, which means if my phosgene goes up by plus X, what did my carbon monoxide go down by? It went down by X. And my chlorine? Same principle, down by X. Do you need to show this conversion process? Okay. You'll probably find that most people don't show this conversion process. Why? Okay. It's a relatively simple conversion that you did multiple times over, theoretically, in 151. You should be comfortable with that conversion process. If you are not, what should you do? Write it out. Okay? Make sure that you understand what's going on with that, because if your balanced chemical reaction coefficients change, is that going to change the multiplier on the X? Yes. So you need to watch out for that. How do we spell ice? That was supposed to be an easy question. Maybe it was too easy. How do you spell supercalifragilisticexpialidocious? Okay, how about ice? Thank you. Okay. E standing for excellent. Embarrassed to say I just saw Sonic 3 this weekend. Excellent. Okay, one person gets the reference. Equilibrium. Do we know the equilibrium concentration of our chlorine gas? Nope, wasn't given to us. Okay. We don't know the carbon monoxide. Do we know the COCl2? Yeah, we know it was 0.08, right? Do you know what X is now? 0 plus X has to equal my equilibrium concentration, which means X is. Why is that valuable? Now what do? Do I know 0.1 minus 0.08? Yeah, what did it equal? And if we look at that given information, neat. Okay. So the point of the ICE table is really to organize your logical flow, to track how your calculations run, and it can help you navigate what's happening in those systems. Make sense? You guys been using ICE tables yet in Alex? Yeah. Not yet? Ooh, okay. Here's your intro. This is a relatively smooth one. Okay, it gets worse. Sorry. Questions? Okay. Sorry, was that no? Okay. This helps to explain why we almost never get 100% yield. Really what this is just referencing is that equilibrium in general explains why we almost never get 100% yield. Okay, because we always have a reverse reaction contributing to that system. Okay, so value of our equilibrium constant is experimentally determined, so we've got to go through and run those calculations to figure out what's going on. Okay, what does the value of the equilibrium constant tell you about the relative amount of reactants and products at equilibrium? Blue box, thank you guys for jumping right into it, or maybe you guys are talking about something else. But it looked like you were answering the question. Words from your face, answer the blue box. So if we go through and look at this, there's a couple approaches. One is just looking at that expression, products over reactants. So I would look at the magnitude of my number. Okay, so if we look at the very first expression, KEQ is 1.3 times 10 to the 7th. Okay, this is an interesting statement that I hear a lot of people say, well, that one is obviously big. I would argue that's not obvious. That's dealing with powers of 10. Nobody likes powers of 10. And that becomes a challenging thing to understand and manipulate. If you struggle with recognizing the size of those numbers, a positive power of 10 is big. A negative power of 10 is small. Right? And try and hold on to that. So if we're looking at that first expression, if I have a big K value, what does that mean about the ratio of my products to reactants? I have to have a lot of products because a big number shows up in the numerator. Okay? So that first expression says I've got tons of products and I have very few reactants. If we move to the next K expression, that's now a small number. Okay? For it to be a small number, what does that mean? Okay. For me, I would look at the products again. The products have to be smaller than the reactants so that I get a small number. Right? The flip of that is I have more reactants than I have products. What about a negative number? Because negative 1.3 times 10 to the 7th is a really, really small number, right? What would that mean if I had negative 1.3 times 10 to the 7th? Powers of 10 can be dangerous. Let's get rid of the powers of 10. I have negative 1. What does it mean if I have a negative 1 for my K? Yeah, if it's making you feel uncomfortable, you're probably on the right track. What does it mean that I have a negative number? I did something wrong. Why? What do the concentration of my products and reactants have to be? They have to be positive values. I cannot get a K that is negative. Okay? Which brings up an interesting point, because when we're saying small, we're not saying negative. It's a small positive number. Okay? So in this system, what's that relative change? When do I switch from being big to small? Yeah, exactly. When's that switch? When is that switch from products being bigger than my reactants to my reactants being bigger than my products? When does that happen? Okay. When K is really small, my reactants are really, really, really big. That's when my reactants are really, really big. How do I switch from being a big number to a small number?
When you have a higher reverse reaction than you have before.
The reverse reaction just means I have more reactants if I have a higher reverse reaction. The switch between products being dominant versus reactants being dominant is the all-powerful 1. Okay? Because if I am larger than 1, what does that mean? I must have more products than reactants. If I am smaller than 1, I must have more reactants than products. So when we're talking about this difference between large and small, it's all relative to the number 1. If you are smaller than 1, you're reactant favored. If you're larger than 1, you are product favored. So understanding those transition points between those large and small numbers, okay, is really, really valuable. We did the same thing when we looked at rates when we were looking at transition points. How do we transition from one direction to another? That might have also been a different class, to be honest, but I think we had that conversation. Okay? So when we're looking at our KEQ, it's all relative to 1. Okay? And you can sometimes hear it referenced as the extent of the reaction. The larger the K value, okay, the greater the extent the reaction happens, which is a fancy way of saying I get more products. The smaller the K value, the less products I get and the more reactants. Okay, and that sounds a little bit weird because I would argue that is. I'm not getting more reactants, I'm just not making products. Kind of, sort of? Okay. So we've got this question up here. I'll pause the recording in a second. So if we have a K equals 3, we start with 1 molar A, 0 molar B. Draw a graph that shows how the concentrations of A and B change over time as the reaction reaches equilibrium. Okay. So first thing I'm going to do is make some modifications. I hate those arrows. Okay. We're looking at an equilibrium arrow with those changing our directions. Okay. Where would we put A? Well, A, we would start at 1 molar. Where would we start with B? B starts down here with 0 molar. Okay. Have we seen a plot like this before? We have. When did we see a plot like this? This was kinetics. Okay. We're now talking about equilibrium, so you are going to have to make a change to this plot. So what I'll start you off with, okay, is the wrong example. Does that sound reasonable? You want to look at the wrong example and figure out why I'm wrong? Okay. Everybody does that. Welcome to married life. Shouldn't have recorded that. So, what's going to happen to the concentration of A? It's going to decrease over time, and then it should flatline out. What's going to happen to the concentration of A? Or, sorry, B? It should increase, and then it should level out. Right? When we're talking about kinetics, our conversation was really back in there. Right? All we cared about was those initial changes. When we move to equilibrium, what do we care about? We care about out here where theoretically that's now flat. Okay, so we're looking at different parts of our plot. Does that make sense? Okay, this plot is wrong. Okay, there are some things that you could do to adjust and fix it, and that's what I want you guys to talk about. Okay? This is a challenging question, so I'm glad to kind of see that it gave anxiety to everybody else too. Okay? So, where should we start? Because I can show you, we already talked through we say is draw some lines. Okay? We need to be a little bit more thoughtful about our approach. Okay? We're being asked about equilibrium. Let's write down what we know about equilibrium. What do we know about equilibrium? K equals products over reactants, which equals 3, which would also be B over A. Okay? Some people were like, well, that means I have more products than I have reactants. Why? K is larger than 1. Great. Do better. And that's usually where people struggled a little bit. Okay, we can do better. We can say B is equal to 3 times the concentration of A. Okay? What is the B representing in this expression? Do better than concentration, because it's not just concentration. It's concentration of the product. Do better. Say again?
After the reaction, at the end of the reaction?
After and end of the reaction become problematic because what we established with the answer to this is it's dynamic. It's constantly moving backwards and forward. Our reaction doesn't stop. It just the rate of the forward equals the rate of the reverse. That's a neat thing to say in a mouthful, so we call it something else. We call it equilibrium. B is the concentration at equilibrium. A is the concentration at equilibrium. So if we're looking at our plot, we would absolutely expect the kinetic part of this, A to go down, B to go up. The part that we're being asked about isn't what's happening necessarily outside the box. It's what's happening inside the box. Once I have achieved equilibrium, what happens? Okay. B must be 3 times as large as A. So if we look at the plot that I've generated, what do we think our K would be? It's not going to be 1. Sure looks to me like B is approaching where A started, and A had a concentration of 1. So my K expression, products, numerator is 1. What is my A concentration approaching? 0, which means I'm looking at 1 over 0, aka non-defined or infinite. Okay? We've got a number larger than 0 divided by a number approaching 0. That's going to equal a very large number. What is it supposed to equal? 3. So I have to change where these things end. Okay? So how do we change it? I need to know where that caps out. Lower it. Okay, lower what? Okay, let's lower the B concentration. Where should the A concentration be? Slightly increased, okay. Okay, now what we could do is fix our kinetic side to match those. Right? So that at least visually sort of matches, but we can do better because we can quantify. We can quantify because we know exactly the value. There's another value or another expression that we should be able to recognize that we know. What is the concentration of B plus A? Someone said it. 1. We're capped at 1 molar. If we look at the coefficients in our expression, we can't get any higher than that. Okay. Why is that useful? What can I go through and do? This isn't calculus. This would be algebra. B equals 1 minus A. Now what do I do? Sub back in. 1 minus A equals 3 times A. 1 equals 4A. And I get A equals to 1/4. So what is my concentration of A at equilibrium? This is 0.25. Okay. Before we go back and do B, are you tracking all the math? Yes. Yeah, okay. Once I know what A is, what do I go back and do? Plug back into either expression, and I'm going to get B equals 3/4, which means that B line comes out at 0.75. What is 0.25 divided by 0.75? 3. And there's our happy-go-lucky plot. Kind of make sense? So what we're trying to do is recognize where we're being asked a question about. Okay? For me personally, it was draw it however I felt and just see what happens and then start to put kind of numbers into it. That's the process that we just walked through. Do you understand? We all on the same page?
Can you explain it again?
Okay. So when we're going through and looking at this system, I'm going to erase all that. We know our K is equal to 3, and we know 3 or our K must be products over reactants. I can rearrange that into this expression. Okay, the B equals 3 times A. That's powerful because now I know the concentration of B. Okay, and I know it must be larger than A. So what I could go through and do within my lines is just make B larger than A at equilibrium. When am I at equilibrium? What's the rate of change of my concentrations? Zero. This is my equilibrium. That tangent line, can't even draw a tangent line because it's flatlined. Okay? That's what I'm being asked about. Right? So I can ballpark 3 times A as best as I can potentially guess. Right? But since I actually know numbers, I should now quantify exactly where those things are. Prove that I actually know the meaning of what's going on with K. That quantification process takes a little bit of a struggle because right here we have 2 unknowns, okay, with 1 equation. Back to algebra, that's an infinite number of solutions. The one extra piece of information is that A plus B is confined to equal 1. That comes from this all being 1-to-1 ratio and knowing my starting concentration. If my starting concentration is 16, what do I have to do? A plus B is 16. Okay? Because that's my cap. I can't have any more than what I started with. Conservation of matter. Okay? With those 2 expressions, we'll flip it this time. We could say A equals 1 minus B. Positive I'm going to get yelled at for that, but I'm going to do it anyway. Okay? Because I didn't have to solve for B. I could solve for A. So A equals 1 minus B. I now take this information, sub it back up into my first equation. B equals 3 times A. Whoops. Sorry, that's why you shouldn't have done it this way. Good job, Mike. We have to do a little bit more algebra. Minus 3B. Add 3B to each side, what do we get? We get 4B equals 3. We get B equals 3/4, also known as 0.75. I can then take that B, sub that back into whichever expression I want, solve for A, and I know the A value. Easy. Make sense?
Thanks.
Okay. And if you wanted to review that, that's around 30 minutes. Okay. Pictorially, okay, what we might think happened. So what we're seeing up here in the top is what we might think. This is what I initially drew. Okay? Because when we think about what we did in Gen Chem, we just made products. Oh, it just makes products. Oh, son of a... At least I didn't finish the statement. Okay? Just makes products, just makes products. But what we have to realize is that our reactions don't just make products. Okay? They're limited based off of that K value, that equilibrium. Which means when I look at the final state, I'm going to get a mix of my reactants and products in that final solution. It never goes all the way to completion. Kind of, sort of? Okay. Equilibrium constant is related to the change in Gibbs free energy. Okay, so we've got some magic equations here. Okay, these are magic equations that I would highly recommend you write down on your note sheet. I also want you to take a little bit careful look. Okay, for me personally, the one that I would take a look at is this one right here. This is a thought game question. So ignore the blue box, all this stuff. Does that red expression look familiar to anybody? That looks an awful lot like the activation energy, our Arrhenius expression, right? Okay. But it's not activation energy here, we're talking about delta G. And if we think back to our Arrhenius expression, we had EA for the forward reaction. Delta G is talking about this energy. That's delta G. If the Arrhenius expression gives me EA, how the hell am I going to get delta G out of it? Why is this related? Delta G isn't talking about a rate constant, it's talking about the equilibrium constant. And we look at the equilibrium constant, what are we looking at? The rate of the forward equals the rate of the reverse. In my plot, all I'm looking at is the activation energy for the forward reaction, right? How about we look at the activation energy for the reverse? What would the difference be between those two activation energies? That's the delta G. That's why this looks like it's tied back to the Arrhenius expression. It is. Okay? So you could go through some fancy algebra using the Arrhenius expression and rate forward equals rate reverse to get you to this KEQ related to delta G. That's kind of mathematically neat. It's also unnecessary for the sake of the course. But I want to make sure that you can recognize its utility and that you can tie these theories to each other. Make sense? Calculate the value for delta G for each reaction at 298 Kelvin. Well, each reaction happens spontaneously at this temperature. Okay, so it's now a question of just plugging and chugging and getting some numbers. So spend some time, plug and chug. So if we go through, I've got some numbers written up here, and there's some debate over the size of the numbers. We'll talk about that in a second. So in theory for the red, you should have gotten, we'll just go ballpark 40,000 joules. 40,000 joules is a really big number, right? So what do we typically represent delta G in? Kilojoules, and we could drop in that decimal point and get 39. Kind of make sense? Okay. Did the question specify which unit? No. So which unit should you pick? The easiest one for you is the unit you should pick. If you're given freedom, do whatever's easy. Okay? Make the grader suffer. Okay? In theory, the grader should provide feedback saying you should fix your question so that I don't have to grade it this way. Make sense? Okay? If we move to the blue one, you should get a number, ballpark 24,000. We'll come back to that ballpark in a second. Again, our unit comes in as joules. Okay. Now we want to do a quick sanity check behind these. KEQ, if we look at the first one, what I'm calling the red expression, that's a number that is larger than 1, right? And if it's larger than 1, which side of the reaction is favored? Products, which would mean our delta G should be. This goes all the way back to the thermodynamic stuff that we talked about. Remember, we're dealing with spontaneity for individual reactions. And if our products are favored, we're looking at a delta G that is negative. Look at that. Conveniently, the numbers came out right. We're looking at a negative value. Okay, if we go through and look at the other one, the blue KEQ, we have a delta, or a thing I'm pointing at, equilibrium constant. The equilibrium constant is less than 1, small number, which would say what's favored? Reactants, which would mean our delta G should be positive, and I wrote a negative. What should that mean? Okay, we now have an internal check that we did something wrong, and we need to go back and verify what's going on. Because that something wrong could be as simple as a sign change. It could also mean you put the wrong number into the expression. But by using that as a quick sanity check, you can verify what happened. And in this case, it should have just been the lack of that negative sign. And we should be looking at a positive. Okay? I did say ballpark for both of these. Okay? I looked at the work for two groups, only for the red one. The blue one's probably got the same issue. Okay? And the two groups for the red One had 39 kilojoules, the other 40 kilojoules, 40 and change kilojoules. 40.6 kilojoules. Right? And looking at their work, the only thing that I could see that was different was right here. The inclusion of an extra significant digit, 8.3145. Okay? That change of that number drastically changed, or drastically, it's not that drastic, but changed the output that we're seeing a pretty significant difference in those numbers. Right? On an exam, particularly because everything you do, on your quizzes, because everything that you do is show your work, okay? That's not going to matter. What you're going to get is probably, if the key said 40,000 and I saw 39, I'd be like, dang it, okay, what happened with your work? And I'd go back and look at the work. Work looks spotless? Okay, if you just fat fingers on a calculator, that's fine. Okay, I get it, we move on. Does that make sense? So why talk about this as a potential issue if it's not going to show up in your quizzes? Do you have, say, an online homework system that it grades you based off of significant digits? Yeah. Make sure you know what R values they're using, because it's going to change your output, and that could result in Alex marking you wrong for something that you actually know how to do. Make sense? Okay. This is insanely frustrating. I apologize. There's nothing I can do about it. Okay. Anywhere. You have to use the numerics that are used within whatever those calculations are for an online system. You just have to. Make sense? In theory, it also showed up in 151 if you're doing molar mass calculations, depending on what periodic table you used. Go ahead.
So for the KEQ that's less than 1, we got a negative delta G. So can we change that to a positive only because the KEQ is less than 1 even in the map?
No, so that's where we got to be careful. We went through, we had a negative, okay, but when we look at the KEQ says it should be positive. So what does that mean we do? We double back to our work to figure out what went wrong. In the particular case, assuming this person did the calculation actually right, in this particular case, the only thing they did was they left the minus sign off. By leaving that minus sign off, they came to a negative number. You bring the minus sign back in, what happens? It becomes positive. So we're not making it positive just because, we're making it positive because we went back and checked the work. Does that make sense? So we're using that magnitude difference to help us predict what happened with our sign. We good? Okay. So, free energy and equilibrium. We've got a nice little fun table. Okay, depending on your preference, this table may be something that's useful for a cheat sheet or not. If you're looking at a KEQ larger than 1, what does that mean about your delta G?
So if K is bigger than 1, it's positive or negative.
Okay? And you talking through that is lovely, as exactly what I wanted to hear. Okay? K bigger or smaller than 1? How many different choices do you have? 2. It's either positive or negative. How many choices do you have? 2. It's either spontaneous or non-spontaneous. How many choices do you have? 2. These are all 50-50 questions. But when you string enough 50-50 guesses together, it takes the odds from a student getting it right away from 50-50 and dropping it to blind guessing being down at 0.25%, okay, or lower. So you need to be real careful with your signs as you go through and navigate these things. Okay? Again, me personally, I would make sure I've got these things noted and correct. Okay? For me, I need to see what K equals every single time. I want to see products over reactants every single time so that it helps me keep straight what these numbers mean. So if I'm larger than 1, I have more products than I have reactants. Okay. What does that mean for me? I would also go through and look at an energy diagram. More products than reactants. My products are favored in this system, which means my delta G is negative. The reaction direction that happens spontaneously, forwards. More products or reactants at equilibrium. The last question on this is one of the very first that I answer, right? Because it helps me keep straight what's going on within those systems. What happens if my K is less than 1? Okay, I'm looking at a positive delta G. What direction happens spontaneously? The reverse or the backwards. More products or reactants at equilibrium? Reactants. It does not take much to throw you out of your loop for the logical thought all the way through. So be very careful and, I guess, explicit as you navigate these things to ensure that you don't accidentally make a mistake and swap your sign from positive to negative, either in the calculator or your thought process. We good? Equilibrium and rate. We went through and did this solve. What did we say equilibrium was? We'll just say, yep, that's exactly what we said it was. That it was equal to the rate forward equals our rate reverse. What is our rate forward? K forward times the concentration of our reactants. What is our rate reverse? K reverse times the concentration of our products. We can drop all the rate stuff out, group terms. We'll get K forward over K reverse equals concentration of products over the concentration of reactants. K forward is a rate constant. K reverse is a rate constant. And a constant times a constant, divided by a constant is a bigger constant. Okay. And we get our fun expression of equilibrium. So they are related to each other. Okay? We can track them, but we have to be really, really careful when navigating them. Okay? Come on, do what I want. Do what I want faster. Okay? This is on Canvas, keeping up with the Ks. There's lots of K expressions. Okay? Remember we talked about that very first one, our big K related to delta G. Looks really similar to our Arrhenius expression. Okay? And that has to do with how you would set those expressions equal to each other to be able to navigate and solve for those individual pieces. Okay? You need to keep them straight and organized. Okay? This is on Canvas. Do you think you need all of these notes? Yeah? Then it shows up on your note sheet. If you don't think you need them, that's fine. You don't need them. But realize you've got those two different dynamics going on within it. Okay? Depending on when you choose to retake quiz number 1, you may be thinking kinetics and thermodynamics simultaneously. That could lead into confusions between these Ks. Does that make sense? So if you get done with your retake earlier, your brain should now be fully into that equilibrium system, and hopefully it'll be easier to navigate. Make sense? Oop. We did that. Come on. There's our review equilibrium constant. We follow that. Our ratios, forwards, reverses. Sorry, we're moving faster on that. Okay. Which direction would have a larger rate constant? The forward or the reverse? How do you know? All right, we got another blue box at the bottom. Spend a minute or two at your tables trying to figure it out. So we've got a lot of questions being asked kind of within this. Which direction has a larger rate constant, forward or reverse, and then how do you know? There's a couple approaches to it. I almost always universally will go to pictures, then I will to formulas, but the formula helps out a lot. Whoops, I didn't want to erase that yet. If we're looking at the rate for a chemical reaction, right? Rate equals our rate constant times a concentration. So if I'm considering the rate of a reaction, that K has to factor in something. I can change concentration, but is that the only thing that affects my rate? If I have tons of pens, right? Tons of pens and caps, do I get reaction? No. What do I need? I need a proper orientation. Does the concentration of A factor in an orientation? No. Where's the orientation get factored in? The rate constant. What else do I need? Ooh. Chemical reaction. Okay. Okay, there it goes. No, it didn't work. Why not? I need an energy. There's an activation energy that is also tied to that chemical reaction. Okay, where is that activation energy factored into my rate expression? Also into the rate constant. It's all tied in that single thing. So why does that become valuable to me? Well, I can go back to my chemical reaction and I can start talking about the activation energy. Okay? If my activation energy is small, what is that going to mean about my rate? Should it be a faster rate or a slower rate? It should be faster. Okay? The only thing I've changed is activation energy. So smaller activation energy and I got a bigger rate. What does that mean my K must be? It must be bigger. If I look at a larger activation energy, what's going to happen to my rate? Slower. What does that mean my K must be? Smaller. So I can use that activation energy to help me predict those differences between those individual systems. Does that make sense? Okay. What else could I do? Those of you that are entirely math brains, you could just go right there and look at your K expression. Okay. We had a K expression. Okay. If we're looking at this, this is spontaneity. Products are lower in energy than our reactants, which means our K is big. Go back and look at those previous slides where we defined that. If our products are lower in energy than our reactants, we're looking at a large K value. Why does that become important to us? If I have a large K value, which rate constant is bigger? KF must be bigger than KR or K backwards. Okay? Make sense? So there's multiple ways in which we can manipulate and understand where those numbers are coming from. Okay? And I was saying to look backwards. You didn't even have to look backwards. It's in the friggin' orange box. Okay? If I'm looking at a negative delta G, what does that mean about my K? It's big. We've got that information there. But that means holding all of those pieces of information at once and being able to manipulate them. Can you do that? If you're even questioning whether you can do that, what should you immediately be doing? Practice, or you've got a cheat sheet. Start getting this information down and organized on that cheat sheet to simplify your approach when it comes to a quiz. Okay? We've got our same energy activation, this diagram again. Quite frankly, I don't know why it's here, so I'm just going to skip by it. Ta-da! Okay. We've got our energy profile diagrams. So we just talked about the one where our negative delta G, products are lower in energy than our reactants, products are favored, large Ks, all of those pieces. You could have looked at the reverse, where we're looking at an endothermic reaction. Products were higher in energy. This slide summarizes a lot of content and attaches pictures on top of it. Right? I would argue, as some people have already numbered or mentioned, this is probably a good cheat sheet slide. Right? Again, it comes down to what you're comfortable with and what you want to navigate as you move through it. Man, the clock is slow. There's a good question. We'll end with this and start with this on Wednesday. How will the equilibrium constant change as the temperature increases? Okay. A couple different approaches that you can go through to do this. Brute force, you also have an elegant method because you have the delta H and delta S. Okay? So 2 approaches to tackle this question. We're going to pick up with this question Wednesday. I would recommend you try both approaches.